Mm-hmm.
Okay, where do we want to start? Which one?
Let's see. I kind of wanted to start on 1D.
Okay, 1D would be f of g of x.
Yeah.
All right. So let's see. Our functions are, let's see if I can figure out how to do this. Okay. So we have f of x equal x over 2, and we have g of x equal x minus 3, and we have h of x equal x. All right, and they want f of g of x.
Yep.
Is that D? No. Yeah.
Yeah.
D is f of g of x. Okay. First of all, if I said to you, what is f of 4, how would you figure that out?
Plug in 4 for x in the equation of f.
Okay. So that's equal to 2, right?
Yeah.
Okay. Now what would you say if I said, what is f of x plus 1?
Plug in x plus 1 for x.
Okay. So that's the scheme. Regardless of how complicated it is inside the parentheses, we're going to plug in whatever we see for x.
Okay.
Okay? So what does f of g of x mean? That means f of what?
It means you plug in x for the equation of g, and what you get for that, you plug it into the equation of f.
Well, when I say g of x is x minus 3. So what I'm really saying is, what is f of x minus 3?
Oh, okay.
Okay? So that's all you do, is when they say f of g of x, substitute whatever the function g of x is equal to, which is right there.
Okay.
And proceed. So what's the answer?
So you would have x minus 3 over 2.
Just like that.
Oh, okay.
What next?
Okay. Let's see.
In fact, everyone on this A section here, 1 through 6, can be done. Always work these things from the inside out. In other words, if we were doing 6B, well, first of all, let me ask you, do you need to do any of these others?
I don't really think so.
Okay.
So I think...
But you do them from the inside out. In other words, if you wanted to know how to do this one, first of all, let's figure out what h of root 3 is. Whatever that comes out to be, plug it in for that.
Okay.
Taking g of whatever number that is, or whatever value that is. It's a lot like nested parentheses. In other words, if I give you something that's got a whole bunch of parentheses nested in that, Well, the way you do these is you start from the inside parentheses. You do that one first. You distribute it, and then you do it. In other words, that's the way you do all these kind of problems, is you work from the inside out.
Okay. I see.
All right. Make sure you know how to do each of these before we leave this section. So if there's one more there you want to do, let's do it.
I don't think so. I think I'm good.
Okay. Yeah, it's pretty straightforward. Once you discover the method, that's pretty straightforward. Okay. About 7, 8, and 9.
Yeah.
Okay.
So,
what does the horizontal line test tell you?
it tells you whether the function is, it has an inverse.
It's whether it's 1-to-1. Well, which is the same thing. In other words, a function only has an inverse if it is 1-to-1.
Okay.
Okay. Let's look at some examples here. If I'm looking to pass the vertical line test, is that passing?
Yeah.
That makes it a function. Now,
Okay.
in order for this function to have an inverse, it has to be 1-to-1, which means it has to pass the vertical and the horizontal line test. Does this function pass the horizontal line test?
No.
No, because if I draw a horizontal line there, I get 3 different values. Now, let's talk about something else. Graphically, what does an inverse look like? Well, take this function right here. Y equal e to the x. You familiar with this? You've learned about e, haven't you?
No.
Okay, let's make it y equal 2 to the x.
Okay.
Just an exponential function. Well, this is 1-to-1 or not?
Yes.
Okay, therefore it does have a function, and graphically that function is going to be a reflection. But it's not about the x or the y-axis, it's about this line right here, which is y equal x. If I were to take this original 1-to-1 function and reflect it about that line, I get something that looks like this, correct?
Yeah.
That is the inverse. All inverses are reflections about that same line, y equal x. And you can't have that if the function isn't 1-to-1. Let's go back and talk about a function that I'm sure you are familiar with. And that is y equal x squared. Is that function 1-to-1?
No. Yeah. Yeah.
No, it does not pass the horizontal line test.
Oh, I get it.
Okay. Now, if I tried to make an inverse of this, even though it's not a 1-to-1 function, and mirror it across this inverse line here, you end up with something that looks like this. Notice that this inverse is not a function because it fails the vertical line test. In other words, you cannot turn a function that fails the horizontal line test, if you look at its inverse, it's automatically going to fail the vertical line test. And when something fails the vertical line test, it is not a function. So y equals x squared, you wouldn't really say that that has an inverse function. What they usually do on these kind of functions is they restrict the domain. They look at only that part of that function. In other words, only when x is greater than 0. And now, yeah, that does have a function, or an inverse, right there. All right. So, if we look back at these problems here, so 7 does not have an inverse function.
No.
About 8.
Yes, it does.
Actually not. See this point right here? That's going to fail the horizontal line test. If I pass horizontal line, there's multiple values right there.
Oh, okay.
How about 9?
No.
And 10?
Yes? Or no?
Well, 10 is an interesting function. 10 looks to me very similar to what, if I did have to draw an inverse function for 8, it would be 10. The problem with 10 that I see is that it doesn't look like a function to me. It's a little bit tough to tell because we can't tell right here whether that fails the vertical line test or not. Not from their drawing. And likewise, it's possible that 8 does not fail the horizontal line test, which means 8 would have an inverse, and 10 would have an inverse. But I think I'm going to go with that. I think I'm going to reevaluate 8. I'm going to say 8 does not fail the horizontal line test. In other words, we can't tell for sure on 8. What if it does something like this? Well, that doesn't fail the horizontal line test, which means it would have an inverse. Okay, let's look at what the inverse would look like. Well, let's draw our y equal x line. And the way you make inverses of these is you mirror it about that line. Okay, so this point right here becomes over here. It's always a little difficult for me to do these conceptually in my head. Let's see. This point here is going to end up also right there. This point here is going to end up like that. So I think we end up with something that looks like kind of like that.
Okay.
Actually, it looks like maybe on the end it must do this. In other words, this has to be the reflection of this line.
Well, how do you know, how do you know which way to reflect it across?
Always reflect as if, in other words, if I were to tilt my page here, which I can't do online, but In other words, this point ends up right there. This point here ends up right there. See what I'm doing? This point ends up right there. In other words, I'm looking at, you know how to reflect over the x-axis, right?
Yeah.
Well, this is a reflection over the line y equals x. And the way you do it is you take the coordinates and switch them. In other words, this point right here had coordinates of 0, 1, right? So this point there, the reflection, has points of 1, 0. So xy becomes yx.
Okay.
And algebraically, that's the way you do it. Now, notice in number 8 here, when I reflected it, I still have this question about, well, does this pass the vertical line test on the bottom here? And I'm going to say, yes, it does. In other words, this right here is not a horizontal line. There is a point whose slope is 0, right there, but it's not a horizontal line. So it does not fail the horizontal line test. And if it doesn't fail the horizontal line test, then it doesn't fail the vertical line test here. In other words, that we're going to say does not fail the vertical line test. Under that reasoning, we're going to say that 10 has a inverse also.
Okay.
Because 10, we're going to say, is a function. We're going to say it does not fail the vertical line test when we look at it. If that doesn't fail the vertical line test, then it's 1 to 1, and it does have an inverse. And we would get it. Let's first of all graph 10. It looks a little bit like this. Now let's reflect that about that line. So if I do it in a different color, it looks something like this. See what it's happening? In other words, you see how to reflect about that line?
Yeah.
Whatever the x-coordinate was now becomes the y-coordinate. Whatever the y-coordinate was now becomes the x-coordinate.
Okay.
All right.
I see.
Now, let's make sure you can algebraically come up with the inverse. If f of x equals 2x minus 3, how do we figure out the inverse?
I have this in my notes. You substitute y for f of x.
Okay. You can always do that. When we use the notation f of x or g of x, it's the same as y. Okay, so those are always interchangeable. It's just that f of x is a little bit more robust of notation than y is. But when it comes to finding inverses, it's actually a little bit better to use y.
Okay.
There's two things you have to do now.
You interchange x and y.
Good. That's the first step.
And then you solve for y.
Exactly. And it's as straightforward as that. And you can do those steps in either order. In other words, you could solve for x and then interchange the variables. But I think it always makes sense to memorize something and do it the same way every single time. So the way I memorize finding an inverse is you switch the variables and solve for y.
Okay.
Okay. So that one was fairly straightforward. 12 is fairly straightforward. 13. Let's look at 13 real quickly.
Okay.
So what's this inverse going to be?
Hold on a sec. You would substitute x and y. Well, you already have y, don't you?
No. In other words, the first step is substituting y for f of x. This is the same function we started with. So in order to come up with the inverse, we have to then apply our two rules. We have to switch the variables, which I've done here. Now,
and solve for
y. What's y equal to here?
Would you do x over y squared?
No. In order to solve for y, we have to take the cube root of each side.
Oh.
So y would be the cube root of x. Or I could write it a little bit better using exponents. So there is our inverse right there. The other thing that's worth knowing about inverses is that an inverse function undoes whatever the function was doing. Our original function, we were cubing x. Well, if I wanted to undo that, I would take the cube root of x. Right? Or if I have 8 equals 2 cubed, and I want to undo that, I'm going to take the cube root of 8, which is 2, to get back to my starting point. Now, you don't actually have to use that logic very often, but it's worth knowing. That's what inverse functions do, is they undo what the function was doing. Division is the inverse of multiplication. Subtraction is the inverse of addition because it undoes what we were doing.
Okay.
The ones that are particularly tough, and you'll notice they didn't put any there, is this one here. Well, if I apply that logic of solving for the inverse, I'm going to say x equal y squared. And then I'm going to solve for y, and I'm going to get the square root of x. But notice that I would get plus or minus the square root of x. Well, in reality, it's plus square root of x only, not the minus one. Because this is not a one-to-one function. Remember, that's a parabola. So I don't restrict its domain. I can't even talk about an inverse.
Oh, I see.
And there are a lot of functions like that, where they're not one-to-one, but if you restrict their domain, you can talk about them. Have you had any trig, Ellen? Refresh me.
Have I had any trig? Yeah, a little bit, and last year.
All right, well, let's talk about the sine function.
Okay.
That is not one-to-one.
No.
So, and yet we do have an inverse function for the sine function. It's called arcsine, or inverse sine. Well, how do we get it? We get it by restricting the function from this point to that point. So when they talk about the inverse sine function, they're only talking about this part from there to there. notice that that part of the function is one-to-one. That passes my vertical line test. It also passes my horizontal line test. And therefore, you can talk about the inverse sine function.
Okay.
Okay? So, just because a function is not one-to-one doesn't mean that you can't talk about its inverse. It just means that you have to restrict the domain in order to talk about its inverse.
Okay.
All right. What else do you want to go over here? Let's see. We're only doing a half hour today. I can do as much as you want, but what else do you want to look at here?
Just really quick, tell me how to do 15.
Okay. (15) is a hyperbolic type function. In other words, if I were to look at this function is y equals 1 over x. Okay? You familiar with the hyperbolic function?
Not really.
Is this function past the vertical line test?
Yeah.
Does it pass the horizontal line test?
Yeah.
Therefore, it has an inverse.
Okay.
And we would get it by taking this function and mirroring it about that line. Well, you can notice that it mirrors about the same way it looks now. So the hyperbolic function inverse is the same looking as its function. Well, here we have 8 instead of 1, and we have the whole thing being cubed. Well, cubing doesn't hurt. Squaring does. Notice that if I look at the function y equal x cubed, this is what it looks like. Okay? That passes the horizontal and the vertical line test. So I can easily come up with the inverse function, and we just did. It's y equal cube root of x. So let's algebraically solve 15. If y equals 8 over x cubed, let's find its inverse algebraically.
Okay. So then you do x equals 8 over y cubed. Then
now solve that for y.
Yeah. So it would be y equals 8 times the cube root of x.
Divided by the cube root of x. In other words, to solve this for y, first of all, let's expand it. It's 8 cubed over y cubed, correct?
Yeah.
Okay, and now we want to multiply both sides by y cubed. Divide both sides by x. And now take the cube root of both sides. There's your inverse function.
Okay.
In other words, you solve it the same way. When you get to 19, 19 is quite tricky. Whenever you're dealing with quadratics and you're trying to find the inverse function, the solution is very, very tricky, and we don't have time to go over it today, and I don't know if you have to do 19 or not, but you can tell that if you switch the variables and try solving for x, you're going to run into an immediate problem.
Mm-hmm. Yeah.
And the answer is actually just too complicated to explain in a minute or two. But
I can just ask about it tomorrow.
yeah, why don't you? You end up treating a constant or a variable like it's a constant. It's really tricky.
Okay.
Hopefully your teacher will explain to you how to do those. And if not, we can talk about something like that next time.
Okay.
All right, Ellen, I will talk to you next time.
All right, talk to you again.
Okay, bye.